Uh,
So as far as demo goes, do you guys just want to, if you could just explain what you set out to do and then
yeah,
what you did and how you did it, that'd be awesome.
yeah. So I will introduce our project first. So our project is like built based on the algorithm of Harris Corner Detector. You can think of it as a game or application that we can you can write down a letter, alphabet letter, and we can let the algorithm to predict which letter it is. So um so first we convert everything to a grayscale, and we do the spatial derivative calculation. Then we structure tensor matrix and use the tensor matrix to calculate the response, which is used for the next step, the non-maximum suppression. And after the non-maximum suppression, we can have the corners. And so it is always a good idea like to pre-process the image first by a filter to filter out the noises. And we do that by a Gaussian filter. The reason why we do that because Gaussian is linear separable. So if we can use a Gaussian filter first, then we do the spatial derivative. We can just do convolutions. So the calculations so everything working on FPGA can be much more like easier. So we can just use the FPGA to do the convolutions, bunch of convolutions.
So can I just make sure that I've understood the goal properly?
Yeah.
So am I correct that you start with an image of a letter?
Yes.
And then you apply a Gaussian filter to that and then deliver it to the FPGA.
We don't have to do
the FPGA. Sorry, go ahead.
We actually did the Gaussian filter in the FPGA.
Oh, okay. So yeah, you just give the FPGA the image, it does the filter, and it will tell you which letter it is based on the output from a corner finding algorithm that you've also implemented. Okay.
Yeah, we did like a KNN like algorithm and a voting algorithm to do the prediction. Yeah, Sam can introduce that more.
Yes, so in the like predict algorithm, we use like two different normal distributions. So like we treat like the image become like, so we treat all the dots become one image and also the separate dot. And also another algorithm called the callback level divergence. So we have like three different algorithm to calculate the probability of the training data set and the testing data set. Then from like we will like combine all of these value and vote in like which letter is more possible letter we are testing right now. So yeah, that's the
yeah. So the convolution part, because the way we did the Gaussian, because we can just like save the kernels, the Gaussian filter, and its derivative along x and y, like two, three kernels. We just store it in FPGA. So when an image come into the FPGA, we can like just use the derivative of Gaussian along x to convolute with the original image. Then we can get the derivative of the image along x.
Okay.
Yeah, because the first step of the Harris Corner is to find the spatial derivative, which is along x and y. So using a Gaussian filter can make it easier.
Yeah, and one thing I would like to include is since the Gaussian filter was symmetric, so we don't worry too much about the conc. So if you do the actual convolution, you have to flip the images along certain axis.
Mm-hmm.
Since Gaussian is symmetric, so we don't need to the flipping convolution. So that's another advantage we have for Gaussian filters.
So when we need to compute the sums of the products of the derivatives at each pixel, we just need to use the spatial derivatives and convolute with the original Gaussian filter again, so we can get a sum.
Okay. So let me just, I want to see if I understand every step of what happens to the image.
Yes.
So you send the image into the FPGA.
It's grayscale.
You send a grayscale image into the FPGA.
Yes.
It does it applies a Gaussian filter to that image, and then applies the corner finding algorithm.
So
did I get that right?
The corner finding algorithm requires so we actually combine these two steps.
Okay.
So the corner detecting algorithm, in order to get the corners, we have to first find the spatial derivatives of the image. Second is compute the products of the derivatives, and the third is the sum up the derivatives. And and a Gaussian filter is used to filter out the noises. It's like a pre-processing thing. But we find out that the filter can actually be combined with all these steps for Harris Corner Detector, because Gaussian is linear separable. So for example, in order to do the first step, do the spatial derivative, we can just use the derivative of Gaussian along X, convolute with the original image. Then we can get a partial derivative of the image along X.
Okay. Okay.
Yeah. So we make it combine, and we don't have to worry about what's Hao said is the flipping thing or derivative thing. We just don't need to worry about that, because if we want to do the derivative along X to the image, we have to use another kernel, right, to calculate the pixels before it and after it. So if we can, because the Gaussian kernel is just 3 by 3, we can just calculate by our hand the derivative of the Gaussians and store it in a 3 by 3 kernel, which is in the FPGA.
Okay.
Yeah.
Okay.
So if Hao can go through the FPGA steps, maybe it can help you understand the process.
Yeah. So basically, as we talk about, we have an image processing image from HPS, and we send to the FPGA through SRAM.
Okay.
The SRAM, the same SRAM we use for Lab 3, like handshake, this kind of thing. So the same technique. So once it's sent to FPGAs, one more thing we did is we have a rounding zeros, a padding of zeros for the image, because we are using a 3 by 3 image, which means we need one more. You can think about one more columns and one more rows, because otherwise we have holes outside the picture. So we just adding 0 outside the picture, so which will be a 32 by 32. Basically, what the image we have is 30 by 30, and the window we have is 3 by 3. So the image we send to FPGA through SRAM was 32 by 32, and after that, once we know everything was read into the M10K block, we do all the things processing, as Sean said before, we have for all the filters like GX, GY, and all things. So we have to basically do two times convolution. Like first time we convolute with GX and GY, and second time we calculate. We have another round of convolution to convolution with GXY. So that's a 2 round of convolution, this kind of things. So after all the convolution results, we have the results for we can think about the R value, what is used by Harris Corner, it's a score, you can think about that. So it's pixel by pixel. So we think about once we have a specific pixel for all 3 values. So let me just include this. So if we need a R value for certain pixel, we need 3 values, which is IX squared, IY squared, and IXY. So 3 squares. So you can think about it's a matrix. So top left was ix squared, and the diagonal was iy squared, and the other diagonal is the ixy. So we certainly 4 values need 3 values total, because the other is the redundancy. So with all, so we calculate these can be parallel on hardware on FPGA. So we basically parallel computing on this. Then we just calculate our values like 1 by 1, 1 pixel by 1 pixel based on that. So then we send all the R values, then save them into SRAM, then send back to HPS to do further, maybe we can say it's a recognition procedure with Sam talk about is KNN and a little bit voting algorithm. We kind of combine with them because it's not really a machine learning, really strict machine learning application on that way. So.
Okay. And you said these are 30 by 30 pixel images, correct?
Yes. All the pixel was 30 by 30. And I can explain more about why we choose normalize the value from 0 to 1. Because, you know, the grayscale usually from 0 to 255. And we do some demonstrate experiment on it. So if we use 0 to 225, the value of R will be huge. Like you can even hold in like I think 64 bits or something like that. And also you are losing some position because you are you are losing some decimal points after the decimals. So the reason we choose to use to normalize it, basically all the values will be 0 to 1 is based on this question. And then also in this way, we can use 27 by 27 multiplier for DSP block, which is for each multiplication, we will only use 1. If you use really long multiplication, the DSP block resource will be still a limitation on our application. So that's why we choose to normalize all the grayscale pictures. And we after several experimentation, we think 621 will be a good implementation for us. So that's why we finally use 621 floating point representation for our calculation. So that's all the flow on the FPGA stack.
Okay.
And we can have a small demo. And we also have a MATLAB application to read the images. Maybe Sam can talk about more about this. So it's make our all code flow more complete in this way.
Yeah. So let me do the demo first, and we can explain more about our design. So I made an app by MATLAB. So we can select the image we want. So let's try. So it will return the image array. So when we start our program,
is it control, Sam? It's not CTRL, is it? Yeah.
Then it will first ask which letter are we going to test. So this is basically the answer. Tell the computer, say, okay, right now we're testing the letter L. Then we'll enter the array we just got from the MATLAB. Then it will show the image. Then when we press the reset, then it will predict okay, then it found the right answer. The letter should be L. Then it will represent the image. Yeah.
So when you say that you're testing L, the FPGA doesn't know the right answer.
Yeah, it doesn't know the answer.
It just knows if it got it right.
Yeah, the ground truth value for the computer know it's going to come.
Yeah, but it really depends on you. If you just input A, but the prediction is L, it will just Sam, you can show that.
So if I told the computer this is the image, is the letter A,
right?
But it give me the answer is L.
I see. Okay.
It will
And is
fail.
this showing it? Are the red dots there showing the output of the corner?
Yes.
Finding
The
out?
Corners
corner
from
output
FPGA.
non-maximum suppression.
This is the corner from,
Interesting.
yeah. Like
Um,
the result we got, the corner is more than this dot, but we do the non-max suppression, so it gives us the highest value from each 3x3 matrix.
Okay. Okay.
Yeah. And our computation time for doing the Harris Corner algorithm is about 0.5 milliseconds. And we compare the computation time from the MATLAB, and MATLAB is about 10 milliseconds. 10 microseconds, right? 10 milliseconds.
Okay. Okay.
Yeah.
and also,
So yeah,
there's yeah. Sorry, Sam. Let me.
no,
just-
you can go.
There's because the comparison is not really fair because we are running on MATLAB, which is on a PC. You know, the clock frequency is much faster than what we have on the FPGA, which is I think only 50 megahertz.
Right.
For the PC, I think at least gigahertz level. So that's another difference between I think 40 times difference between that. So even with this kind of 40 times difference about the clock frequency, we still have a speed up. I think the more fairness to compare these kind of things is to use the cycles, number of cycles instead of time. This maybe we can include more in our lab report. So that's another way we can show our hardware on the PGA do accelerate for this application.
That's a good observation. Yeah.
Yeah. Probably a fairer way to do it would be to use C rather than MATLAB.
Yeah.
Because C is optimized down to the machine cycle level, whereas MATLAB is an interpreter.
Yes.
But still, the speed up is quite significant, and that's great. Interestingly, another group that was comparing Python to FPGA got about a factor of 20 speed up also. So that seems to be a sort of a consistent number going from an interpreter to hardware. But just as interesting is how much energy did it take to do the calculation? You can calculate that by the power use of your laptop versus the power use of the FPGA.
Okay.
Times the time it took to do the calculation, right?
Yeah.
And you're going to find that's a huge number.
Mm-hmm.
The FPGA is much better. The power estimator tool will allow you to estimate your design power. All it takes is the compiled code. It doesn't take anything else. You could do it now.
Could be a cool metric to include in a final report. Yeah.
In a final report, yeah.
So just because it'll be impressive.
So for
That's
the
right.
FPGA, I'm sorry.
Go ahead.
So the how intensely red the dot is a measure of how important the corner was. Is the color encode the cornerness, so to speak?
So for the red dots was the Harris corner we have after non-maximum suppression. So Sam we have another for the a prediction phase. We have maybe Sam can introduce more about the voting. He has a different weighted calculation for the voting, I think.
Okay, I mean, why are those red and the other one's pink?
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 Where is the pink?
I think that's the screen reflection.
Yeah, they're all the same color.
Yeah,
they're all the same color.
they are the same color.
Yeah.
Okay,
Yeah,
never mind.
Yeah.
Never mind.
Yeah, so obviously our prediction cannot be 100%, but it should be a good phase.
Yeah.
If you guys,
I use
If you guys
MATLAB
interested,
to
you
test.
guys maybe can write one letter. We can demonstrate.
So
If
I
not-
can write a letter real quick from
Yeah, maybe you can demonstrate to show we didn't like cheat on this. You can write it.
I'm not sure if it works, but let me take a screenshot.
One thing I want to explain is because we are writing on this kind of thing, so maybe a little bit noise, more noise, or interaction with this. So maybe it can success, maybe not, but
Let's see. Oh yeah.
Hey, look
bingo.
at that.
Yeah,
That's awesome.
Yeah, because like we use MATLAB to calculate the overall letters accuracy. So we found like the L, P, and V, and Y is more like accuracy later. I think one of the reason is also like the training database we use for the Z is not really good. So the Z later has a very low accuracy.
So this is showing how good of a job it does recognizing each of the different letters?
Yes.
Yeah.
Okay.
So we asked some friend to write a letter for us. We do write some letters. The one thing we've discovered why Z have a poor job is someone has a how can I say it?
The way we write is
slash
different.
on the
Yeah, there's a line in
like
here.
someone has this one, someone don't have that one, makes the prediction really hard.
Okay.
And also if some letters is really similar to the Harris Corner side, let's say maybe E or F, maybe they will sometimes cannot do that because
Sure.
you know,
Yeah.
E and F is really close, just and also some really clear neighbors. So that's what.
Did you do a confusion matrix?
Oh, we didn't try confusion matrix, but we can include that in our report.
Sure, that seems like you have all the data for that.
Yes.
Yeah.
And one thing is that we kind of don't have a really huge, in my opinion, don't have a very huge testing training data set. That's why maybe our prediction is not as good as like a 90 or something like that. If I think increase a little bit of training set will help a little bit. To be honest, Harris Corner is not a really machine learning way to recognize these kind of letters.
Yeah, I think the age detection will be much better than Harris Corner.
I mean,
but because actually we have the kernels, so it can just be just small modification of the system to like do the edge detection. We can just change the kernel.
Okay.
So it will be easier to do the.
And also, all our code on the FPGA set was parameterized, so we can easily change it until we have, unless we have this enough resources.
Yeah, if we have more resources, we can just make the mini image larger, like to 50 by 50 or 60 by 60.
Sure.
And other thing I would like to include is we can, so for this demo, we only include like 0 or 1, so like a black and white images. We do test it. Basically the same thing. We can choose to use the grayscale pictures.
Yeah, grayscale.
It still can find the corners, but since it's not like a ladder, our application board, so cannot do the prediction phase. So that's why we didn't show. If you guys interested, we can find a grayscale image to find the corners to compare with, and we will print out the corners maybe on the screen or something like that. But maybe that require a little bit modification of our application. So since it's changed from time to time.
Okay. But if you were to put in a grayscale image that wasn't a letter, it would find the corners of that image. Just of course, the prediction doesn't make sense anymore. Okay.
And also we can include the results on the lab report to say we can also do grayscale images.
Yeah, that'd be good.
We test that. We
test it, but right now we might have a little bit modification in order to show that.
Sure. Yeah. That's fine. Awesome. Well, that's really cool. Seems like you guys built something that works.
Yeah.
And also Because we have a resource limitation on Friday. We have like
Yeah,
Yeah.
we just rewrite everything.
everything for the like 2 or 3 days. We spend like almost all of the time on this project. So that's why we are glad it works finally. So that's our
after we use the M10K, the logic utilization reduced to 60%.
Were you running out of registers? Do you have things stored in registers previously?
Yeah, because as Professor Bruce said earlier, we have a really complex this was indexing for the arrays that will make a lot of lookup tables to implement that.
Sure.
Yeah.
Okay.
But changing to MTK blocks require like the timing this timing thing. So we just rewrite the state machine.
Yeah, that's a big refactor.
It's a big refactor, and it's a pain in the neck. But
so our group, our final thing is like we if there is a like something like modism on the chip, now this will help our debugger. Will very helpful because the signal tab sometimes really didn't help.
Yeah.
Because you have memory limitations. You don't have you cannot run too many samples. You cannot see too much like different lines how interpret it.
The only other thing you can do is you can output 2 signals plus a trigger on I/O pins directly to an oscilloscope and debug using the oscilloscope rather than signal tap. And that requires no memory. It does require physical access to the FPGAs, which we couldn't manage this semester.
Okay.
Also, you can only look at 2 signals at a time, so you have to think very carefully.
Which 2 signals is much important.
Yeah, you could compile with 20 signals being output, but you can only look at 2 at a time.
Yeah.
Plus a trigger.
Okay.
Drive you nuts.
Oh.
Well, thank you guys. That looks great.
Okay.
Thank you.
So
thank you.
Also, thank you for the great semester.
Yeah. We also are graduating this semester.
We are